Alright. So in this packet, the answers are in it. This is the practice exam that AP released a few years ago. So it doesn't have like what percentage of people got each question right, but if you look on the very back page, the answers are back there. So number 1 was C. Number 2 was D. 3 was C. 4 was B. And 5 was C. So we'll go over those. Okay, so number 1, you're integrating. It is U substitution, you're right. You're going to integrate this using U substitution. So I know I have to do U substitution because I have a composite function. I have one function inside another function. So just like that's my clue with derivatives that I have to do the chain rule, it's my clue with integrals that I have to do U substitution. And you call the inside U. So the derivative of that would be 3, which we don't have. So we have to give ourselves a 3 out on the outside and balance it with a 1/3. So if I rewrite this, it becomes 1/3 cosine U du. The 3 and the dx together make the du. So now when I integrate this, cosine will become sine. The du goes away when I integrate because it's a derivative, and when you integrate a derivative, those cancel out. And then we just plug back in for u. So 1/3 sine 3x plus c.
What's the one that you use, like that one little sheet of paper? And I think it's like negative sign. Was that like something else?
If you take the derivative of cosine, it's negative sine. It's always tricky to remember. The way I remember it is that when I'm taking the derivatives of the cofunctions, cosine, cosecant, cotangent, the derivatives are negative. And then if I integrate to a cofunction, so like my answer is, like I'm integrating, like right here I integrated and I got sine. Well, if I'm integrating and I'm going to get a cofunction, I'm going to get cosine or cosecant or cotangent, then that's negative. I always have to stop and think too. But just remember, you have to be able to take the derivative of this and get back to that. So the derivative of sine is cosine. Alright. So that one was C. Alright, so number 2, the limit as x approaches 0. You should always try substitution first. So on this one, if I try substituting a 0 for the x's, I get 0 over 0, which tells me that there's a hole in the graph. Remember that the limit exists at a hole.
See, I thought it was non-existent.
It would be non-existent if we got a number other than 0 over 0. Because then there would be a vertical asymptote and the limit wouldn't exist there. Or if we had, certain piecewise functions. But for a rational function like this, if we get 0 over 0, there's a hole. And the limit exists at a hole in the graph on a rational function. So what we have to do is factor and cancel. So on the top, I could factor out a 2x cubed, which would leave me with x cubed plus 3 in the parentheses. And on the bottom, I can factor out an x cubed, which would leave me with 4x squared plus 3 in the parentheses. Right? So then I can cancel out the x cubes that I factored out. And so now I can substitute. So now when I substitute 0 for x, I get 2 times 3 on the top. I get 3 on the bottom. So I get 2. Limits were the very first thing we did, so it's been a really long time. But we talked about whenever we get 0 over 0 that we should try factoring or rationalizing or something so that we can substitute. All right. Number 3,
When we put in 0, sorry.
we plugged in 0 because we were doing the limit as x approaches 0.
Oh, and then this is outside. Okay.
Yeah. Right. Okay, so number 3, the function f defined above for what value of k is the function continuous at 2. So for a piecewise function to be continuous at the point where the pieces break, you have to be able to get the same thing when you plug 2 into both pieces. In order for it to be continuous. That's what that means. Continuous means both pieces are equal when you plug in 2 for x. So if I plug 2 in for x on the first piece, I get 4 minus 6 plus 9. So I get 7. That has to be what I get when I plug 2 in for x on the second piece. So when I plug 2 in for x on the second piece, I get 2k plus 1. So k would have to be 3. Right, piecewise functions are only continuous if each piece is continuous, which these are. This is a parabola and a line. And then where your pieces come together, they have to be equal. So basically it's so that you can make a smooth transition from this parabola to this line without a break between them. Alright, number 4. Number 4, I'm going to rewrite this like this. This one's actually a little messy just because it's a double chain rule. This cosine cubed means that the whole thing is cubed. The cosine of 4x is cubed. So you've got a composite function, which tells me I have to do the chain rule. And within that composite function, you have another composite function. So it's like a double chain rule. So it's kind of tricky. You got to keep them all straight. So the big outside, so I'm going to call this the big outside, and the big inside, and then the little outside, and the little inside. So the big outside, like the overall big function, is a cube function. So we bring the 3 down to the front, change it to a 2, leave the inside alone. Then we have to multiply by the derivative of the big inside. And so that's when we do the derivative of the big inside, we have to do the chain rule again. Because the inside, big inside, also has an outside and inside function. So we have to do the derivative of the outside, which the derivative of cosine is negative sine. Leave the inside alone, times the derivative of the inside. So it should be b. Because you're going to have 3 times negative 4, which is negative 12.
So when you're finding the derivative of a function, it's like negative sign for cosine specifically?
Yes.
And then the problem we did earlier?
When we integrated,
it's positive.
when you integrate cosine, it's positive, but when you take the derivative of cosine, it's negative.
Okay.
Yeah. So I should get B. Okay, and then the last one, number 5. The function has a relative minimum at what x value? Okay, so you can only have relative mins or maxes wherever the first derivative is 0 or undefined. So if I look at the first derivative here, I'm going to get 6x squared minus 6x minus 12, which if I factor out a 6, is this. And if I factor that, get this. So there are two places where I could have a relative minimum. There are two places where this would equal 0 at 2 and -1. The only way for me to know which one is actually the relative minimum is to make a little sign chart and see what's happening to our slopes around those two places. We know the slopes are 0 at these two places because those are what makes the derivative be 0, and the derivative tells us the slope. So if I plug -2 in here, I get positive, negative, negative, which is a positive. If I plug in 0, I get positive, negative, positive, which is a negative. If I plug in 3, positive, positive, positive. So my slope goes positive, negative, positive. So I would have a minimum at 2. Alright, so we'll call it quits for today. And go start watching some of those,
Yes.
of the other ones, especially the free response, because we haven't done any free response in here.
Okay. Sounds good. Thank you.
You're welcome.